Thank you all for joining this presentation. My name is Bill Chow, Product Marketing Manager at MathWorks for our code generation products. And today in this presentation, I want to talk about deep learning in MATLAB and how you can take your designs from MATLAB all the way down to embedded code running on your NVIDIA Jetson. So MATLAB is a deep learning framework. Uh, and it's an environment where you can design your deep learning frameworks along with other parts of your algorithms, vision algorithms, um, uh, and other pre-processing and post-processing algorithms. And MATLAB helps you to manage large data sets with different sorts of tools. We also have tools that help you to automate image labeling, have easy access to models, and also have pre-built training frameworks. Now, with these deep learning networks, we have facilities to help you to accelerate the training of these deep learning networks with GPUs that are either locally on your machine or out in clusters or all the way up to the cloud. And so we help you to scale as your requirements are needed. And once you are happy with the trained deep learning network and with the rest of the algorithm, we have a new product called GPU Coder that helps you to compile the entire application to CUDA so that you can run it on the NVIDIA GPU of your choice. Everything from desktop GPUs to embedded NVIDIA Jetson. So to introduce MATLAB a little bit, we'll kind of talk about it within the example of using transfer learning. So in this workflow, we'll need to work with large amounts of training data. And for example, you might be trying to label different sorts of vehicles, cars, trucks, large trucks, etc. And one of the things that you'll need to do is also work with reference networks, everything from AlexNet to VGG to GooglyNet. So how might that piece of code look like? So for example, if we're working with a CFAR data set, one of the first things we need to do is to set up the training data set. So here you can see we start by bringing in the CFAR 10 training set. We have set the 5 categories that we want to identify. One of the things that we provide is an abstraction called image data store. And what this does is helps you to work with large amounts of data fairly easily. So these data sets could reside on your local machine. It could be in a database or some other big data file system. And once you bring that in, you'll most likely need to do different sorts of data augmentation. You might need to split these data sets, shuffle and rearrange it randomly. For example, in this particular case, maybe we only need 500 images of each class. So there are functions that help you to do that fairly easily. In addition, you might need to do other sorts of data augmentation. You might need to read in the files, resize these images, and things of that nature. So once these data sets are ready to go, then you'll need to load your reference network. And we help you to do this with fairly simple one line of code. Here you see net equals AlexNet, which helps you to load the AlexNet framework into MATLAB. And if you take a look, AlexNet has 25 layers. Everything that you see, ReLU layers, fully connected, and so on and so forth. And in this case, for example, since we want to identify 5 objects instead of the many others within the AlexNet, we can go ahead and modify the network structure very easily. So in this case, we're going to remove the last 3 layers, and then we're going to add 5 additional layers, 2 fully connected, a ReLU layer, softmax, and finally a classification layer. And you'll notice that the second fully connected layer, at the end, we will end up with the 5 categories that we want to identify. So once you go ahead and make these changes, you can very quickly see the updates to that network structure. And finally, at this point, we want to go ahead and start training. so that we can learn the new weights in order to classify the 5 different objects that we're looking at. There are many other training options that we won't quite get into, but I just want to put that out there. And of course, with MATLAB users, one of the biggest advantages that people talk about is the fact that there are many, many different visualization and debugging tools available for you to take a look at. And this is true when you work with deep learning networks. So we have tools that help you to take a look at filters, your activations, deep dream, and there are many other tools to help you to visualize and debug the deep learning networks as you work on it. So for example, as you go through, if your deep learning networks are not converging for some reason, there are tools to help you to visualize it and debug it so that you can better understand what is going on. And we have many, many different examples that ship with our products to help you get started. So once you set everything up, you start training it. There are various ways for you to scale so that you can train your deep learning networks even faster. So you might start by adding more GPUs or more powerful GPUs. You might then want to work with multiple GPUs and eventually scale up to clusters and even the cloud through Amazon EC2 instances. And as you go through these different steps, it's fairly easy to change your MATLAB algorithm. Training options, which I showed a little bit earlier, has different parameters for you to tweak these different options. And the one that we're looking at is execution environment at the bottom. So if you set it on auto, it will take a look and start using the GPUs that's available on your local machines. But as you go through, you can start changing it so that you can use multiple GPUs. And then all the way, if you set that last parameter to parallel, then you can start using clusters and Amazon EC2 instances that's available to you. So once you've done, you've trained your deep learning networks, the next step is you want to use or you want to deploy your deep learning networks and any vision algorithms, pre-processing or post-processing algorithms onto a GPU. So we recently launched a new product called GPU Coder, which automatically helps you to compile your MATLAB algorithms and applications to run on NVIDIA GPUs. So GPU Coder supports, of course, deep learning networks. It also works with vision and image processing algorithms that you might be using. And we also have support for signal processing communications. If you work a lot with FFTs, for example, that's something that is also supported. So for GPU Coder, how do we take your MATLAB algorithms and then compile that into CUDA? So there's kind of 3 steps. CUDA kernel creation, memory allocation, and minimizing data transfers. So when we take a look at creating CUDA kernels from your MATLAB algorithm, we're doing various things. Like if you're writing loops within MATLAB, we have loop optimizations that can turn those into CUDA kernels. We take a look at dependency analysis, and we also map MATLAB algorithms to NVIDIA accelerated libraries, for example, cuBLAS, cuDNN for deep learning networks. So we try to make the generated CUDA code as fast as we can. Looking at memory allocation, we map to various CUDA structures, everything from local to shared to global memory. So we map it to the most appropriate one for the fastest performance. And of course, data transfers, if not done properly, can totally kill the performance of your algorithms. And so we have various data dependency analysis and dynamic mem copy reductions to help minimize the amount of data transfers between CPUs and GPUs. So what's an example of generating these CUDA kernels? So you could be, for example, working with what we call scalarized MATLAB. So here on the left, you'll see a little for loop. And if you look inside of it, you'll see that the operation is operating on each element of a particular array or matrix. So in this case, the generated code will look like that. That's a little code snippet. And if you notice, we take care of all the CUDA mallocs, CUDA mem copies, and CUDA free at the end of the day. Here's the actual CUDA kernel that was generated from the Saxby algorithm. And if you look inside of that CUDA kernel, you can see the fairly complicated or set of CUDA code that is generated to help you to parallelize that. Another kind of way of writing MATLAB is what we call vectorized MATLAB algorithms. So here we also have a for loop, but again, if you look inside of the for loop, these variables z, for example, is actually a matrix. So we're operating on a fairly large matrices, as you can imagine, for both z and count. And this example is actually a Mandelbrot algorithm. And when we generate code, again, it looks similar to the previous example. We take care of CUDA mallocs, CUDA mem copies, and whatnot. The for loops that you see here is also mapped so that the for loops is operating on the CPU. But inside of the for loops, we're calling different sorts of CUDA kernels. In this case, something called CUDA kernel 3. And inside of that, these CUDA kernels are being launched onto the GPUs to help you to parallelize and speed up operation of that. And in this particular case, we were able to get a 10 times speed up once we are running this on the GPU. So I talked about memory management a little bit earlier. We support, of course, CUDA malloc and also the newer CUDA malloc managed. And if you're working with image processing and computer vision type algorithms, there are opportunities for us to do even more to boost performance. For example, we have a design pattern in MATLAB called a stencil operation. In this case, we're in certain instances where, for example, in image processing, you're operating on a convolutional kernel. When we convert this to CUDA code, we take advantage of shared memory so that we can maximize coalesced memory access with this particular dot product. And so this helps us to increase performance so that you can run these algorithms much faster. And this is all done automatically by GPU Coder. So we took a look at vision algorithms, which a lot of our customers have kind of asked us whether or not we would be able to boost performance with GPUs. And you can see a whole bunch of these, everything from fog removal to distance transforms, stereo disparity, and surf feature extraction. You can see quite a bit of speed up when you run these on GPUs. So coming back, in terms of taking your algorithms, what does the workflow look like for you to take a MATLAB algorithm and then run it onto NVIDIA Jetson? So there might be a couple of steps along the way. In the first step, you might be working just within MATLAB itself. You might have some MATLAB test benches for you to go through and make sure the algorithm is operating as you expected it. And of course, within MATLAB, in addition to having your deep learning networks, you might have vision algorithms, pre-processing or post-processing algorithms that you can all run together within one environment and run your test benches that way. So once you go through and make sure everything is performing as you expected, one of the next steps you might want to do is take a look at unit tests. So in this case, if you have access to GPU on your desktop, then one of the first things you can do is get your algorithms to run on your desktop GPU. So at this point, you can use GPU Coder, and there's something called a build type option. But what that is it tells GPU Coder, hey, you should generate code for something called a MEX file. So MEX files are executables that can operate within MATLAB. And underneath within the executable, there's actually generated CUDA code that has been compiled so it can run within MATLAB. So using GPU Coder, you can generate these MEX files and still within the MATLAB environment, run your algorithms um, both on, of course, the CPU as well as your desktop GPU to see how this performs on a GPU. So you can still reuse all the test benches and other visualization tools that's available within MATLAB. And once you verify that this is working correctly, one of the next steps you might want to do is essentially move from the MATLAB environment to your C or C++ environment. And let's say your end application is going to be in C or C++. Still, you would be on your desktop GPU, but this is moving us one step closer. At this point, within MATLAB, inside of GPU Coder, you can change the build type to generate a .lib file. And so once you generate the .lib file, you can migrate that, incorporate it into your larger C or C++ application, and run this on your desktop GPU just to make sure that everything is performing as you expected. And assuming everything works out there, next step could be looking at how to migrate this onto your Jetson platform. So again, coming back into GPU Coder, you could generate a lib file, but at this point, you would want to cross-compile it. So um, you can cross-compile it on the host with, for example, the Linaro toolchain. So going through all these different steps, I wanted to give you some examples of a couple of these different steps. So on the first parts, we'll take a look at running your generated CUDA code as MEX files within MATLAB for unit testing. So to do that, I'm going to talk about a fog rectification algorithm. So this is not a deep learning network, but rather a computer vision algorithm that you can use to clean up, for example, an input foggy image. And once you clean up the input foggy image, that can then be passed on to, for example, a deep learning network to identify um, uh, traffic signs or other things that you want to work with. So this could be a pre-processing algorithm for your larger object detection algorithm. So switching over to MATLAB, here's the MATLAB desktop. We have the tool strip at the top, providing various different commands. On the left, this is the current folder, showing you all the files that we have. Here's the MATLAB editor, where we can work with various files. The command window here lets us execute various commands. And on the right, this is the workspace showing us all the variables that we're working with. So to start things off, I'm going to show the image that we're working with. So our input image here, as you can see, is a little bit foggy, and we want to clear it up like so here on the right. So that's our output image. And with this cleared image, we can feed it to the next stage. So the algorithm that we use to clean up the image is the fog rectification.m file that you see over here. There are several different stages in here. First step, we're going to get the dark channel estimation from our input image. Next, we'll refine it using anastrophic diffusion. We'll then do some restoration with inverse Kashmir's law. And then the remainder of the algorithm is running histogram stretching of the image. And we went through until the end of the file. So we just used this algorithm and we were happy with it. So at this point, let's go ahead and generate code. So coming up into the apps tool strip, we'll navigate down and we'll find the GPU Coder app. So here's the GPU Coder app. And the first thing we need to do is, of course, we need to specify the file that we want to generate code from. And we can select more than one file to generate code from, but in this case, we'll just have one file to start. Next thing we need to do is to specify the data types and sizes of our inputs. So we can enter this manually. You can see here we can start putting in the data types and sizes. But another way is actually to use the all-define feature. So here I'm going to enter a command that will execute the file that I'm trying to generate code from. If I click on the all-define function, you can see here that MATLAB automatically infer the data types and sizes of the inputs. You can also specify functions or scripts in here, and it will automatically detect the data types and sizes. Next step, it's recommended that we check for runtime issues by creating a MEX file or MATLAB executable. I'm going to skip this step for now. And finally, we can go ahead and we can specify what we want at the output. It could be source files, static or dynamic libraries, or in this case, I'm going to select a MEX file or MATLAB executable. So what this is it will generate code, compile it, and let us run it within MATLAB. So here it is, finished code generation. Let's take a look at the code generation report. On the left here, you can see our original fog rectification.m file. And let's take a look at the generated code. Here is the header file, fog rectification.h. And within that, we have one function, fog rectification. So here it navigates over to the source code, the .cu file. And if you come down, you'll see that it takes care of specifying all the data types inside of your temporary variables and other variables that you're using. Takes care of cuDNN, and it's also going to generate all the calls to CUDA memcopy, as well as calling the various CUDA kernels. That's going to help us to go through the rest of this algorithm. And then here you can see all the the comments that you had within your MATLAB file. This is transferred over as well. So here we're getting the stage 1 where we get the dark channel estimation from our inputs. And it's calling various kernel 2, kernel 3, and so on and so forth. Here on the left, you can see here's links to the various CUDA kernels that we generate code from. If you click on each one of these, it will take you to the right place in the .cu file. So that's the code generation report. And coming back, I'm going to take a look. And I'm going to run a helper command or helper script here, benchmark foggy image. And what this script does is it's going to help me run down a little bit. Here, help us to benchmark execution running on the CPU and the GPU. And you can see here we're going to run it 10 times. So here we can take a look at the performance. So again, this is the input and this is the output. When we use the CPU, it takes about 35 milliseconds for us to run through this. But running the same algorithm on the desktop GPU that we have here took a little bit less than 7 milliseconds, which means that we have approximately a 5x speed up using the GPU. So that's a quick look at GPU Coder. So let me go ahead, clean things up. So coming back, I just showed an example of that unit test step within your workflow. If we then jump towards all the way to the right, what would that look like in terms of taking your MATLAB algorithms and running on your final Jetson platform? So let me show you an example of that. And here we're going to talk about a lane detection example. And this particular lane detection example, we're going to use AlexNet. We're going to modify it for us to identify the different lanes. There'll be some post-processing as well, because once we identify where the lanes are, we'll need to um, mark it up with the to mark up where the lanes are in yellow, as you can see over here. And we'll display all this in as a part of the an output video. And actually, for this particular example, the input to the to our system will be a video that we captured earlier. Coming back to MATLAB, let's take a look at this. This lane detection example is another shipping example that comes with GPU Coder. So I'm going to run a script to help set things up. Set up the NVCC paths. We get the pre-trained network as well. And the deep learning network that we're working with, what it's doing is the input is going to be a video, and I'll show you that video in just a moment. And the deep learning network here is going to be able to take that input video, identify the left and right lanes of the road. And from there, we can then map out and draw the lane markers for into our output video. So the network that we're working with has been modified from AlexNet. So it has 23 layers. The difference here, the network architecture has been modified so that the last few layers has been replaced by a smaller, fully connected layer, as well as a regression output layer. So that's what you see over here. Our input video is going to be this particular video. And as you can see, this video was captured from a camera mounted at the front of a car as it speeds down. And what the deep learning network is going to do is identify the left and right parts of the lane, and then we'll be able to draw the lane markers for us to identify it. Okay. So in the previous fog removal example, I showed using GPU Coder app up here in order to generate code. The equivalent can also be done in the command line. So in this case, I'm going to show the command line version. Here, I'm going to use a couple of commands to set up the configurations for GPU Coder, and then I'll call the cogen command to generate code for our algorithm over here. And the algorithm that we're actually going to generate code from is called detect lane. And inside detect lane, first of all, it's going to go through and it's going to, for each time the video frame comes in, we're going to run it through the deep learning network. It's then going to output the lane coefficients, from which point we can figure out if we did find the left and right lanes. And then using different algorithms, computer vision and math algorithms, we'll be able to find the trajectory of the lanes, and then we will send it out to be mapped in the output video. There's going to be some transforms involved. But in any case, this is the function that we're going to generate code from. So coming back here, I'll go ahead and generate code. So the code generation was successful. Let's take a look at the code generation report. Here's detectlane.cu, the source code. And if we come on down, we'll see that's an initialization. And over here, detect lane. Again, it takes care of specifying the input data types and sizes. figures out all the different variables that are needed within the function. And then coming further down, it starts going through. And here is the part where we will call the deep learning network in order to figure out the left and right lane coefficients. And again, all the original MATLAB comments are translated over as comments in the generated code as well. So we're going to bring all of the generated code over. So I'm going to close that out. Another file that we'll also need is we need a main function so that we can compile it for the Jetson TX1. So this main underscore lane net.cpp, this was handwritten, and it's also included as a part of the shipping example. But if you come on down, let's take a look at main. Here's the main function. Oh, I should mention that to read in the video files, we're making use of OpenCV. So we have that header file installed, mentioned at the top. And within our main function, at the beginning, we're going to use video capture to bring in a frame of the video at a time. And then coming further down, in this big while loop, we're going to read in the data, we're going to write the data, and so on and so forth. And actually within write data, let me scroll back up. It's over here. In write data, as you can see, this is the part where we call the detect lane function that was just generated. From there, we'll be able to identify whether the lanes were found with the means, the standard deviations, the left point and the right point. And from there, we will call these other two subfunctions add lane in order to actually add the visualization of the lanes at the output. Okay, so at this point, I'm going to go ahead and open a terminal. So all the generated code is contained within this CodeGen folder. And I'm going to copy that. And in my console, let me navigate over. So I'm going to copy the lib folder over to my Jetson TX1. I'm going to copy to a webinar folder. Okay, so that's done. In addition, I'm going to copy several other things. First of which is the Caltech AVI file. I'm going to also copy the handwritten main function that we just took a look at. And finally, there's also a main makefile that we need to copy over. Now let me connect to the Jetson TX1. Okay. And as you can see here, we have all the files that were copied over. So let me go ahead and first of all, we need to run the makefile here in order to build the first library for detect lane.cu. Okay, here we go. So here we have the library file that was just created. Next, we need to build the main function, and that's going to help bring in the library that we just created. Okay, so we just built the executable. So let's go ahead, and the final executable is lanenet. So we can launch this, and we're going to bring in the AVI file that I showed earlier. So here's the input video, and as you can see, the left and right lanes are being identified, and we're going to draw the lanes in yellow as the vehicle goes down the road here. And as you can see, when we run through curves, it's going to be able to identify where the lanes is curving towards. And that's the lane detection example that's running on the Jetson TX1. Okay, so let me clean up here. Okay, so coming back. So we showed you a couple of examples of what it would look like within MATLAB. And at this point, you're probably wondering about the performance of the generated code. So we took a look at running AlexNet on a Jetson TX1, and we compared it to C++ Cafe. As you can see here, it has the performance curve that you see here. These are frames per second, and along the vertical axis and the horizontal axis is the batch size. And with GPU Coder, here you can see the performance curve performing better than C++ Cafe. Towards the larger batch sizes, you can see that working performing much better at about 20 to 35%. And of course, with GPU Coder, the code is automatically generated so that you don't have to work with writing all sorts of different code. And if your algorithm changes uh, as you work on your project, you can very quickly change the original MATLAB algorithm, run through your tests, see everything, make sure everything passes, and then regenerate code, and that's already up and running. So we also took a look at the Jetson TX2, and over here you can see, just for comparison, the original or the same performance curve from the Jetson TX1. We're at batch size of 128. It was near very close to 200 frames per second. On the TX2, with its improved performance, GPU Coder also improved along those dimensions as well. So here you can see the performance curve approaching 300 frames per second for the larger batch sizes. And of course, we've been talking a lot about the Jetson TX2, but the generated code from GPU Coder is portable across NVIDIA GPUs since it's CUDA code. And so if you were to run this on, for example, a desktop Titan XP GPU, comparing it with a couple of other popular deep learning frameworks, GPU Coder performance is quite a bit stronger in those instances. So kind of wrapping things up, MATLAB is a deep learning framework that enables you to work with deep learning algorithms as well as vision algorithms and other sorts of pre-processing and post-processing algorithms. Helps you to manage large data sets, has tools for automating image labeling, giving you easy access to models and pre-built training frameworks. We have tools to help you to accelerate the training of your deep learning networks with GPUs that either reside locally in clusters, or even all the way up to cloud. And finally, with GPU Coder, you can take all of your design that you created within MATLAB, compile it to CUDA code, and run it on the NVIDIA GPU of your choice. Everything from desktops all the way down to Jetson platforms. So with that, I want to give a shout out to take a look at some of the deep learning examples in MATLAB. There are links that you will be able to access when you download this presentation. Take a look at GPU Coder, and also we want to give a shout out to the NVIDIA registered developer program, Jetson TX2 and TX1 dev kits, and also our edu links. So thank you all for attending this presentation, and we'll switch over to our question and answer segment.